Hello, check. Hello, check. Yeah, good morning, Mohit Vishnu garu.
Hello, sir.
Yeah, good morning, sir.
Good morning. నేను చెప్పిన వినిపిస్తుందా?
Yeah.
Okay.
We'll start within few minutes, sir. Students are joining.
Yeah.
Right, thank you. Mr. Balaji, please start the session.
Okay, sir. Good morning, one and all. And the dignitaries presented here, a warm welcome to you all. Myself, Balaji, and I am from A2EE. Now I am here to initiate the second seminar in Student Seminar Series. Let me give you a brief introduction about Student Seminar Series. As a part of developing our students in various technical domains, we are inviting the students from those who are pursuing masters, those who are in research works, to deliver their talk on their workouts and research. So as a part of this, we are having the second seminar in Student Seminar Series. And we have a guest speaker, and seminar chair will introduce our guest speaker. Forward to the seminar chair.
Good morning, everyone. Now I would like to introduce our speaker, Mohit Vishnu Kate. Received the B.Tech degree in Mechanical Engineering from RGUKTN in 2018. After which he started working as a research assistant at the Department of Aerospace Engineering at the Indian Institute of Science, Bangalore. During his time here, he worked on various projects involving package delivery using UAV system, localization of heterogeneous robot teams in GPS-denied environment, and multi-sensor fusion to avoid obstacles for a fast-moving multi-rotor for the autonomous operation in an unknown cluttered environment, etc. Currently, he is pursuing his graduate studies at the Collaborative Robotics and Intelligent Systems Institute, Oregon State University. His current research interests include the use of reinforcement learning to produce real dynamic behavior using the first principles of legged locomotion. Thank you. Balaji, you can continue.
Wasting time. Let's pass our mic to our speaker.
All right, everyone. Am I audible? Can anyone of you confirm, please?
Yes, sir.
Yep. So I am Mohit. I'm pursuing my master's as described at Oregon State University. I graduated from RGUKT Newsvideo in the year 2018 with a bachelor's of technology in mechanical engineering. I'll be talking about my journey throughout in the field of robotics, right from what I did in RGUKT and during my assistantship at Indian Institute of Science and what I'm pursuing right now. So I'm sorry I don't have a lot of pictures or details about whatever research or projects I completed at the university, at RGUKT as such. But I'll try to fill in all the gaps and show you what was the exciting journey which I took. And this particular presentation will have a lot of videos. This would help you all to understand what were the problem statements. So it's not only about legged robotics. I'll talk about mobile robots. I'll talk about UAV systems. I'll talk about legged robots. But yeah, so it'll be a journey throughout. I'll start sharing my screen. Yep. I hope my screen is visible to all. Okay, so let's begin. So these are some pictures when I was at RGUKT Newsvideo. So I started working in the field of robotics just by manipulating a few sensors, which were basically IR modules, motor controllers, etc. I started working on four-wheel drive robots to solve line following challenges, which you can see towards the left side of the screen. It's a picture taken from the internet. I don't have the actual picture of my robot. So these were some robots which we made for one of the convocation exhibitions back in 2016-17. These were my colleagues back there, and we received some appreciation award from our previous chancellor, Raj Reddy Garu. And talking about some work, this is one of the memorable projects which I did, in which it involved manipulation of servo motors to build a humanoid robot. This was also funded by SDCAC and Convocation Committee back then. This particular project is interesting because I had a so when I started my journey in the field of robotics, I thought robots were just something which could drive and move around, like you saw in the previous slide. So, but in this later on, I found out like humanoids do exist, and I just wanted to explore a few things. Now, this is basically just manipulation of servo motors, DC servo motors, and we could achieve. I do not have latest videos in which we were able to make the robot walk as well. And this was presented at RGUKT RK Valley in front of the chief minister back then. So after completing my third year, I joined Indian Institute of Science as a summer research summer research intern. And this towards the left, you can see a huge drone which would almost come till the waist length. And this was a drone which I built as such during my internship over here. So I am very proud to say that this particular drone was manufactured end to end from where I've put all my efforts. So so the whole structure, the control systems, so all I got was the batteries and the motors and the flight control board. Apart from that, everything was manufactured using carbon fiber. So back when I was a mechanical engineer, I used to design robots. I used to manufacture them using carbon fiber. And this is one of the videos in which we showed testing of the same. This particular drone has a thrust of 20 kgs, which is pretty huge. And this was kind of unachievable back then because we were intending to build this drone to carry organs. So this would be used as an end-to-end or a last mile delivery system where an organ for a transplant would be picked up from the airport and sent to the hospital, which would be tedious as such. So here my guide was Dr. S.N. Omkar. Uh, he is a professor. He's a senior research scientist at the Indian Institute of Science, Department of Aerospace Engineering. So from here, I worked at this particular lab for 6 months, and then I moved to work with Professor Debashish Ghosh. I worked with, before that, I'd like to talk a bit about my BTech thesis. So after coming back from IISc after my third year, after completing my internship at IISc, when I returned back, I was pretty enthusiastic on pursuing more into robotics. We tried getting into Robocon, but couldn't succeed then. And then I just focused on getting my thesis done. So my bachelor's thesis was detecting speed of vehicles using monocular camera. Here you can see I use a Raspberry Pi on a robot. So I would like to describe the problem over here. So the thing is, you see the blue robot over here, which is actually a regular vehicle on a road as such. And then this particular robot, we call it the police bot. So this will track the speed of the robot and see if they have exceeded the speed or not. If it exceeds the speed, it will go and chase it. It was a rudimentary idea which I could get it working to some extent, but it requires a lot of polishing here and there. So now we draw the region of interest where we want to detect speed as such. And when the robot starts moving, and I just put a very low threshold on speed detection. So even if it moves through that, the police robot will go and catch it. So due to the size constraint, we had to make the other robot stationary. But the police bot here has the capability to go and capture a moving robot as well. So after completing my bachelor's in May 2018, I joined Dr. S.N. Omkar again in the month of June 2018, where I started working as a project assistant. And after working some time in getting small robots done and manufacturing drones, my interest started developing towards making these systems autonomous. So before that, let's go briefly on what I felt robot definition was back then. To me, robotics was just making something work, and I didn't really understand the nuances of it. Later, when I dived into the field, I started getting a proper sense of what robotics was. So a robot here can be defined as an instrument or a machine which can sense the environment, plan how to react, and do something with the environment. So it, if anything, can check all these markers. We would usually group them as robots. So this is what I saw, and this is what I would define currently as robots rather than what we did back then. So we have industrial arms, we have humanoid robots, we have UAV systems, we have the Valkyrie. This is one of the NASA's humanoid robots. You have Warthog by Boston Dynamics. You have other robots which do all these things based on the first principles of robotics. So coming back to the internship era, so I started working here at the UAV lab as a project assistant. And here the task was to implement, so design and implement an algorithm which would, I'll just speed up this video. So which would actually which could be used for package delivery as such. So the basic idea was to put on a camera. So here we mount some payload onto the drone. So we have a single board computer. This is the Ordred XU4, which uses Samsung Snapdragon compute processor. And the drone would take off. So this is manually controlled here. And now we shifted to guided mode, where the drone would try mimicking how humans walk on the road. So we are detecting the road as such and try staying in the center, which you can see the mask over here. And then this particular drone is autonomously traversed to a given GPS point, and it would deliver the box. We were able to achieve this feat for about 1 kilometer because we were only able to do something somewhere about 918 meters as such. But yeah, we could proudly say that we were able to get a drone autonomously flown from one end of the campus to the other end, which was autonomously delivering stuff. And this was back in 2018. So, yep. So this is how it traverses. And then, yeah, after working there for 6 months, I jumped and started working with Professor Debashish Ghosh at his guidance control and decision making lab. This particular laboratory was initially working with guidance of missile systems and aircraft controls. But later on, we planned on participating in the Mohammed bin Zayed International Robotics Challenge. So this particular robotics challenge was funded and organized by the current Crown Prince of Abu Dhabi. So we had some interesting competitions over here. So this particular robotics challenge involved us using multiple or team of drones to do some various tasks. So I was in the team which dealt with challenge 1. I was the team lead for integration and hardware compatibility checks with respect to software. So I basically worked on the hardware as well as ROS. So ROS is a software architecture used to control robots, and it stands for Robot Operating System. So I'll show you a small video on how these challenges were designed. And this is by the organizer themselves. So the challenge 1, in which the UAV had to capture a flying object. I'll enlarge it. Oh yeah. So here we have a rogue drone is what we call, which has a ball, and it would just fly freely in the free space. And we have a team of 3 drones, and here they're just showing 1. So 3 drones, which would then go and detect where this drone is. We do not know any information. We have to detect it using cameras. And then once we detect it, we grab the ball, and then we test it. So this was the turning point, especially when it came to research personally to myself, because we faced a lot of issues, and the problem statement wasn't constant throughout the competition. So here in this particular video, we can see a blue ball being thrown into the box, which was the target then. Later on, the organizers started changing rules for the same as such, and we had to adapt to them accordingly. I'll talk you all through this particular challenge. So the basic idea was to detect a drone carrying a rogue payload and grab it and then neutralize the object. And the other thing was, if there is something being planted, you had to just eradicate it. So here in our approach, we followed a similar architecture. So where we would search, we would try getting drones, we would do color segmentation thresholding, we would create the region of search, blah, blah, blah. This all goes through that. I'll take you all through it one by one. And yeah, so what we did is we took a drone, we had a gripper to it. So one of the grippers was being used to track the ball and neutralize the target. So in this particular image, you can see this is the rogue drone, which has a target attached to it. And we had to write our own controller to detect the drone in the image plane, and then use commands to fly and grab it as such. So the basic idea was to detect, So the basic idea was to detect a ball and then lock onto a region of search there. And once the region of search was finalized, we put a Kalman filter to the ball. When the filter was used to detect ball or the target whenever it wasn't detected as such, or we lost detection due to various conditions like lighting or wind gust, or maybe due to software failure, etc. So this was one challenge in which we had to detect the ball and go through it. And the second one was to pop balloons. So balloons were an artificial way of saying that the enemy has planted something in our territory and we have to neutralize it using drones. So there were 6 to 7 balloons planted in the same arena, where one drone would fly carrying a ball, and which we had to neutralize using one of our drones. and the other drone would neutralize the planted objects, which were the balloons in this case. So we used a SAC-based controller. So the variation, so when we were testing these things, we found a lot of variation in the system parameters, and we had to adapt to a simple adaptive controller. Initially, we were just going with a PID-based controller, and then we thought of using adaptive controller, since it was being robust to the gust or wind or whatever was being thrown away towards the drone. So in our approach, what we did is we tried detecting the path of the drone. Here we used an RNN-based network. A recurrent neural network was used to detect the drone and feed its point, and we used curve fitting methods to detect which path it was taking. And then we had two of our drones which were aligned in a horizontal in a horizontal structure where they would go and attack the target drone, and we grabbed the target. And so we were given 3 drones, so of which 2 were put into neutralizing these targets, and 1 drone was used to neutralize all the balloons. So it would take a grid search path and it would neutralize all the balloons. So this was the final architecture which we used. It looks pretty complex, but it was just simple modules shown out there. And then there is a small simulation of the same, which I would like to show. Yeah. So in this simulation, oh, sorry. So in this simulation, we can see how drones are. So yeah, so this is the problem statement. So you have targets planted. You have an individual drone kept for that, and you have other drones which would be. So this is the. I'm trying to have a full screen. Just a moment. Okay. Yep. Sorry. So we have a rogue drone which is carrying the target. We have other 2 drones which will be neutralizing the target, and we have the 3rd drone which will be trying to neutralize all the balloons over here. So we have 2 drones, and the FOV of these 2 drones are seen here. So whenever there is a ball detection, we can see where it is. And so just now we've missed the ball in UAV 1. And there was a communication protocol between these 2 systems, where each of the drones would localize with respect to the other drone and send data, which would help the UAV to detect it and neutralize it as such. So yep, now we can see the drone goes towards the target, and we try neutralizing it. So this is the target drone. This is where we go approach, but yeah, now the drone has missed it. Now that it sends a signal to the secondary drone to approach the target, since it has missed it to some extent. Now we try neutralizing it, and we have a successful grab in this one. So talking about the 3rd drone, we have a UAV system which is used to detect these markers, and it will pop the balloon. So in the simulation, we simply delete that particular balloon once it is popped. So we delete it, and it's the same thing for other targets as well. So this was the implementation. This is how our mission control worked out. So we had a target drone which was moving in the figure of 8, and the purple lines indicate how we went and approached the target. We weren't really successful when we tried approaching this particular system back in Abu Dhabi, because we had some communication related issues, but that's what we learned from there. So these were our UAV systems. We used the DJI drones, and we had put our own sensors. So this was the NVIDIA computers which we used on board. These are the cameras. So we had a GitHub camera, which was a cheaper variant of the GoPros, and this would send data to the system. And this is what we used over there. These are some real photos, what happened in the competition. So we had the target drone over here. We were trying to attack it. We were successful in grabbing the ball. In this part, in these two pictures, we can see that we have detected a balloon and we have successfully popped it in the next image. So these are some videos from the same. We collaborated with the Tata Consultancy Services and we made some progress over there. So we started taking baby steps by building small drones and just doing simple autonomous takeoff landing. That is where we were. We did not even fly any drone autonomously, and we had to go to the competition in a span of 1.5 years. This is what we were trying to do by simply taking off autonomously, landing stuff, and we tried looking into drop zone markers and all. I worked on the ball detection where I mentioned like previously, we used Kalman filters to detect the ball. So this particular footage was done on board a drone where it would detect the drone using a darknet based YOLO V3 light. And the basic semantic segmentation was used to detect the ball. So here we were trying to follow and chase the drone. So the drone with the ball is flown manually. The drone chasing it is autonomously done, where it is trying to track the ball and approach the target as such. So we wanted to understand the physics behind how the drone would react when it would try grabbing the ball. Would it jerk? Would it fall down? Or what would happen? We were significantly able to develop controllers for that, in which we can see the drone was pretty stable enough. After like 6 months, we had to send another video or demonstration report to the organizers stating our achievements. So here we improved our system pretty much to a very good extent. And so we had made zones for our detection where we have a drone sitting down, detecting the system and giving away the data. We used collaborative drones like shown in the simulation, where we have one observer drone, which is here, trying to send data of this particular drone to our pursuer drone. So the pursuer drone is the FOV can be seen here. It would gently take off once it receives robust commands. So this autonomously takes off. And now we can see the drone trying to reach the target. This was all done autonomously. And we had created a mesh network using some cheap access points as such. So the system would go. So this is why we wanted to use SAC. So you can see this was based on a PID-based controller, which wasn't very robust. But then we developed our own controller based on SAC, and then it went robust as such. Yeah. So this was the team there, and I'd like to show some of the realistic shots what we took when we were at Abu Dhabi. So here we were trying to do balloon popping using one of the drones, and we tried pretty much everything, and it would pop in the second instant. And I'm proud to say that we were the only team representing India over there, and we stood 6th overall. And that is a very great moment because we were able to surpass many good universities like Carnegie Mellon, ETH Zurich, etc., which have proven that they are pretty much very good with respect to drones or robots as such. So here we have this is on challenge 2, in which one of the subparts of ISC had worked, where the drones would pick up bricks and place it on the given container. And we had a UGV which was built in-house, and this would also do the same thing. So the idea of this competition was to enable robots to do day-to-day activities. So the first challenge was basically on the security of any particular region. The second was using robots for building structures. So this is what showed a proof of concept that they were able to do it with a pretty good accuracy. Now, this particular system was developed by the Tata Consultancy Services with the Indian Institute of Science, and we were pretty much we pretty much solved a lot of problems over here. And so these are some of the pictures from the arena where we had to like carry these drones. So there were some UGVs for other challenges. We had our drones, and yeah, that was pretty exciting. So after my time with the particular lab for about 1.5 years, so this makes 2 years of my time at ISC. That's when COVID hit, and I unfortunately couldn't move anywhere. I was in Bangalore, and this is what I started working with a new lab under the guidance of Professor Suresh Sundaram. So this particular lab worked mainly on learning and collaborative assistance, where yeah, so where drones and where team of drones, team of ground robots were used. So in this particular system, we demonstration, we worked with the BotSync laboratories, where we were developing algorithms to segment roads for robot localization. And here we implemented the same on an onboard computer for this robot. Now the robot autonomously traverses through a given path, and it tries to reach the goal. I'm really sorry, there's some problem with this video. Okay, I apologize for the delay. I'll go to the other slide. Yeah. So this is where we used. This was the first time where I was particularly working on artificial intelligence, where it was combined with multi-robot systems. So this particular research paper was sent for transactions on aerospace, and I think it was autonomous systems. And this particular paper deals with using of reinforcement learning for multi-robot swarm, where we were using these systems to search and localize and do reconnaissance sort of missions as such. So the platforms which we tested on were turtle robots. So 3 robots would talk to each other using a regular network, a Wi-Fi based network, and would update and update the target neutralization. So red markers here are targets, and these robots would autonomously traverse through it in a team, where they try to be in the formation and they do not try losing track of it. And these robots would neutralize stuff. We can see markers over here, which was just for our use case, where we would detect it as robot 1, 2, 3 to individually identify them. So yeah, this was basically on team robots. Later on, before finishing work over there, I worked on algorithm which was used on small quadcopters, where they were able to fly for 5 meters per second, which is pretty fast for drones, using multi-sensor fusion techniques, and we tried demonstrating it in simulations. So this particular project involved us avoiding obstacles using just camera and LiDAR systems, and we were able to detect pretty much everything in clutter, and we were able to control the drone and send it to the given target. So this particular system was tested in an environment in a simulator called Gazebo, where we tried using realistic environments and tried solving the problem. We tried looking into realistic approaches, where we used it in Microsoft Air simulators, where this particular algorithm was tested on the drones to see if it could traverse forest and all. So we tried testing it on the hardware. So we built a small drone, we put a LiDAR. So this is a small LiDAR system over here. Then we had a camera attached to it. And then, yeah, basically to avoid this particular pool. And this was done during the peak times when COVID hit us. And we couldn't really finish testing. We were just able to finish the basic testing of this particular system. And yeah, we got through the whole thing. So after that, we collaborated with a Pune-based company called Garrett, which basically worked on factory automation related projects, where we used state machine technologies to use robots to navigate autonomously in a factory. So this is a small environment which we created at Indian Institute of Science, and we have a team of 2 small mobile robots which would carry stuff and move throughout the factory environment, and then what do you call the targets or the payload was dropped down to them, and they would deliver it to a station. So I'll just speed up the video. So we can see there is a robot arm which will pick up a payload, place it on the robot, and then it goes. So we have a system called the state machine, finite state machines, which were used. And once this particular state was finished, the robot would actually try going to the target. And we purposefully tried walking in between the robots to see if they were able to avoid dynamic obstacles like human beings, because human beings will always be present in the factory environment as such, and we never had any collisions and it was pretty much safe. So we can see him coming to this particular system when it tries to go to the delivery point. Yeah. So that was it. So after this particular project concluded, I applied for my master's. I was fortunate to get into Oregon State University, and I started working at the dynamic robotics lab. So my current research at Oregon State University is on legged robots. So I was pretty much done with mobile robots, aerial vehicles, because I wasn't feeling that enthusiastic, or I wasn't feeling motivated towards solving any other problems. It wasn't it was just because these particular systems were more complex and could be evaluated towards what humans usually do. So these clips are from the 2012 to 2015 DARPA challenge. So DARPA is a defense research agency for the United States of America, and they had asked they invited universities to build humanoid robots to do regular stuff which humans would do. And this is what was the state of art back then. There's a lot of technological jump since then, but yeah, that was that was the era when humanoids actually grabbed people's eye, and researchers wanted to actually explore this particular field. So these systems use classical control methods like PID, model predictive controllers, sliding mode controllers, etc. Our lab works on these controllers, and we have our definite framework which works on reinforcement learning. So reinforcement learning is a part of is a part of artificial intelligence, where we used reward-based functions to define states of the robot, and we penalize it based on what action it took. So it's basically like training a child to do something. So when a child does something wrong, you would punish it or scold it. When a child does something good, you would reward it. It's the same thing. We try using neural networks to do stuff for the same. So here at Dynamic Robotics Lab, so we use our bipedal robot, which is Cassie. So this is Cassie robot, which is developed in-house at Oregon State University, I guess some 4 to 5 years ago, and the development is going on. So these 2 projects were done before I had joined the lab, and yeah, so we started working on reinforcement learning, and we have a couple of world records now. So in the video towards your right, you can see people walking with the robot, and we were able to achieve 5 kilometers of distance with the same robot without stopping or charging or need to charge it, which is a pretty good feat done by students who just finished their masters. So this is what we did, and there are other actions which we showed with the robot. So a robot with a same neural network policy can do different types of gait motions like hopping, trotting, galloping, running, etc. So it is the same network which is used to do that. The only thing is we change the phase input to it, and you can see different behaviors of the robot when it is in the go. Usually neural networks are not susceptible to these changes, but we got them working. So this is one of the achievements done by the lab. Our recent work is traversing blind on staircases. So here the robot does not have any perceptive interface at all. It does not have a camera, it does not have a LiDAR. It tries walking on the steps. We used reinforcement learning techniques to help it understand how it went. So we use a simulator called Mujoku, where we have steps designed and we train the robot to understand it. So it is not only trained for a certain height of steps. You just have the policy trained for, so there is something called dynamics randomization, where the system features, environment, everything is randomized, and you can see the robot is able to learn how to walk after a few hours of training in the simulator, and it uses the same gait motion to come down, go up, and climb, and even if it misses a step, it is able to try recovering stuff. This is where we went towards research. So now I'd like to talk something about my research over here. So my research focuses on making the robot walk in footstep constrained environments, where we used reinforcement learning, which enables gait motions for the robots. You have seen the same. So you see this robot is able to do different things with a similar policy. There aren't many changes, but it is able to do the stuff with that. So here, the research where I come into is we wanted to have targeted footsteps. So in all the other previous videos, you would have seen the robot just going into any environment and then trying to walk around. But we were interested in finding steps where you had constraints for bipedal robots. So for example, steps were solved, but what if you had to traverse among places like this? You had to have stepping stone sort of policies. So this is where we started training an RL-based policy loop, where we had the footstep constraints, and we would give the required footstep length, where the robot would precisely put its foot on the marker, as you can see in the simulator. And this was done in real time, where we put a camera and we asked the robot that this is the region of interest where you should be walking on, and the robot started doing that. So this is something called as a reachability map. So the red zone is the zone where the robot shouldn't step. The green zone is where the robot should step, and the accuracy of the same is pretty good. And yeah, we had markers on the robot. We had markers on the floor. We had a camera which would tell the distance between these two markers to the robot to put its footstep on it. So this is me like looking into the stuff. So here we command the robot to have its footstep here, and we are pretty much accurate about it. So we had an error of about 5 to 8 centimeters, which is pretty decent for these sort of constrained systems. So yep, this is the end of my presentation over here. This is the lab. These are my colleagues and lab members. I work with Dr. Alan Fern over here, and yeah, that's our robot Cassie. Thank you. I am open for questions now. Is someone trying to speak? I am not able to hear anyone.
So, if anyone have any doubts, please ask.
Sir, I have a question, sir.
Yeah, please go ahead. Yeah.
As you have said that so many components are used in making these drones, which includes graphic code and all those things. As the components increases, the weight of the system also increases and the power consumption also increases, sir. So which
True.
results in high rate of battery drain. So how you overcome this issue, sir?
So basically, we tried optimizing everything. So yeah, what you mentioned was correct. We went with some optimal methods to overcome these things. So for example, like you mentioned, you basically don't need to have a graphic card. It's a computer manufactured by NVIDIA actually. So the computer and other systems when we tested the drone without any compute system or cameras or any payload, it would fly for about 20 to 25 minutes. But when we put on all the payloads and the compute power, it dropped down to 15 minutes. So our idea was to finish the whole challenge in 15 minutes, because unless there is a huge leap in the battery technology where we can have lighter batteries and more power from them, we really can't solve that. So the way we went was to use multiple systems as such to optimize the problem, and then yeah, try solving it in a very limited amount of time.
Got it, sir. Thank you, sir.
Sir,
Yeah, please go ahead.
sir, what kind of physical approach that you have been went to get the stability of the drone, sir, to complete the task?
So we did not use filters as such. So the thing is, we used controllers. We used PID-based controllers, and I think your question is more specific to how to filter noise in the drone when it is unstable. So the thing is, when we write our controllers, we have every data sent through something called an extended Kalman filter. An extended Kalman filter is used to fuse a lot of data from various sensors and localize it. That is what would be used to answer your question, I guess. So you can use something like a low pass filter or a Kalman filter or an extended Kalman filter.
Okay.
So yeah, anyone else? So guys, so the basic motivation towards having this session was to push youngsters or people like you to pursue research or research and do projects in this field. It is interesting. And yeah, I would say talk to your professors, talk to your faculty, take problems. So yeah, I know working on these systems is a bit hefty on the cost, and it is not really a normal thing for every individual to do it. None of these things were purchased by me. I was fortunate to have had these given by the institutes, be it RGUKT, be it ISC, or be it this institute. So you have simulators now. You have many other things, resources where you can do all these things. So you can just, if you find that there's a regular problem. For example, you would have seen a lot of people bringing drones for agriculture purposes, but do you actually see them working? No, because it is not feasible. Try getting into nuances of such problems. Try getting into try getting solutions for these problems where you can do stuff. You just need to have a proof of concept, show it in the simulator, show various constraints where these things won't be possible, but try to finish it, try to solve the problem in the simulator. Talk to your faculty and talk to people around. I mean, you can have a startup of your own, you can have a research domain of your own. I mean, that's the main purpose of getting an engineering degree, I would say. So anything else from you people?
sir.
Any further questions?
Sir, is there any challenge you faced while you were representing your first project?
Sorry, what? Could you please come again?
Is there any challenge you face while you are representing your first project from our college?
Yeah, there were a lot of challenges actually. So there were pretty funny incidents also. So I would say it was my first competition in which I had to build a manual four-wheel drive robot, a small robot to travel through various terrains, uh, and we built a small robot to solve a maze as such. We went to Hyderabad to participate in this particular competition, and yeah, it was the first time when one of the other students from our college had come. We were pretty enthusiastic to work on it, and I mean, the team just came fourth, and I still remember it was my second year in engineering. I finished the competition and I came back crying because losing just by one spot when you are doing it for the first time is really painful. But yeah, we came back, we spoke to the faculty members, and yeah, we were able to solve it. And thereon we started doing small other projects, and I'm fortunate to have people like Sham sir, Chakravarti sir, Naidu Babu sir from mechanical engineering who pushed us, who funded us, uh, and they took some risk in getting these projects done, and we were able to do something out of it.
Okay, sir, thanks.
Yeah. Anything else, guys? All right then. Thank you very much for inviting me. I personally would like to thank Chakravarti sir who contacted me and made this event possible. And I'm really grateful to have had such faculty and guides throughout my bachelor's. And I owe them my success to whatever I've done till date. Thank you all. I think I can just log out from here, right?
Thank you, sir, for an exciting session. Now I would like to pass the mic to Vidya for a vote of thanks.
All right, yeah. Cool.
On the behalf of Triple S students, I am glad to be standing here to express my vote of thanks. A special thanks to our guest speaker, Mr. Mohit Vishnu Gadde, for accepting our invitation and for being here with us today. Your thoughts have truly inspired us, sir. And I thank our Honorable Director, sir, Dean Academics, HOD, sir, and Faculty Coordinator of Triple S and supporting faculty members. Thank you all.
Thank you again. I hope to see you all, meet you all sometime soon. Okay, you guys have a great day ahead. I'll log out from now. Thanks.
Thank you, sir.
Thank you, sir.
For the sake of information to the audience, the upcoming webinar will be delivered by Siddharth Pilli sir, research engineer at IIIT Hyderabad, about data science. Thank you all.
Guys, you can leave. This is the end of the session.